Hello, everybody. Welcome back to Mathematical Statistics. We are in the middle of an MLE example. We're going to finish it now, and when we do, we're going to start talking about the UMVUE, the Uniformly Minimum Variance Unbiased Estimator, the greatest estimator in all the land. But first, let's finish our example. We were working with a kind of cute gamma distribution. So we had we didn't have a random sample because random sample means IID, which means independent and identically distributed. What we had were random variables x1 through xn that were independent, but they had different distributions. The ith random variable had a gamma distribution. The first parameter was 2, and the second parameter was 1 over theta ci. Now, c1 out through cn were just positive known real numbers, so they're not part of the unknown parameters here. And as a quick reminder, in case you're watching this video and you're not in this class, when I say X has a gamma distribution with parameters alpha and beta, I mean that the PDF is 1 over the gamma function at alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x, and then an indicator that says that x takes values from 0 to infinity. Whereas other people, when they write this, they're going to mean this PDF with 1 over beta every place that I have a beta. So in here, I'm going to use my notation. And if you have this PDF, the expected value of x is alpha over beta, whereas if you use the other way to write down this PDF, then your expected value is alpha times beta. And in our notation here, the variance is alpha divided by beta squared, whereas you might see the variance as alpha times beta squared. So this was our setup, and we had several parts to a problem. In part A, we wanted to find the maximum likelihood estimator for theta. We did. I'm calling it theta hat. You might use a sub n if you want to stress that dependence on n. But we found last time this was 1 over 2n. The sum as I goes from 1 to n of capital Xi over Ci. And although MLEs are in general not unbiased estimators, this one is an unbiased estimator because if you look at the expected value of this, you can pull out the 1 over 2n, and you can pull the expectation through the sum, and you can pull the 1 over Ci outside of this expectation. And the expectation for us, using this as alpha and this as beta, this expectation is going to be alpha over beta, which is going to be 2 theta Ci. So once you fill that in, this will cancel with this will cancel with this. You'll get a theta n different times and a 1 over n. So you'll end up with 1 over n times theta or theta. So we do have an unbiased estimator for estimating theta for this MLE, even though that's not in general a property you can depend on for MLEs. We did prove that they're all asymptotically unbiased. So if you don't see theta here, you might get a function of theta and some n's. And if you let n go off to infinity, then that expectation should be approaching theta for a general MLE. So part B of this problem was we wanted to compare the variance of our MLE to the Cremier-Rao lower bound for the variance of all unbiased estimators for theta. Because our MLE is unbiased, the variance for our estimator must be greater than or equal to the Cremier-Rao lower bound, and we wanted to know if it actually equaled that Cremier-Rao lower bound or achieved the Cremier-Rao lower bound. For a general MLE, even if it was biased for theta, we still might look at both of these things, but the variance could actually be below the Cremier-Rao lower bound because it's only a lower bound on the variance of all possible unbiased estimators for theta. But we know that in the limit, the MLE is always asymptotically efficient, which means that the ratio of the Cremier-Rao lower bound to the variance is going to 1. So in our case, again, we have an unbiased MLE. We computed the variance already. We got the variance of our theta hat was theta squared over 2n. And now this is where we're picking up the problem. We want to compute the Cremier lower bound and compare it to this variance. So let's find the Cremier-Rao lower bound for the variance of all possible unbiased estimators for theta. You'll recall that the Cremier-Rao lower bound for the variance of all possible unbiased estimators for some function tau of theta is going to be the derivative of that function with respect to theta. We're going to square that and put it over the n-dimensional Fisher information. In our case, the tau of theta is theta itself, so our Cremier-Rao lower bound for theta is going to be, the derivative of that is 1, so it's going to be 1 squared over the n-dimensional Fisher information. Usually at this point, I rewrite this as n times a one-dimensional Fisher information, but that does not apply here because they were only equal if you had IID random variables, and we have different distributions for our different xi's. Even though they all have gamma distributions, they're not the same gamma distribution, so they're not identically distributed. And this means we won't be able to use that computational simplification when computing the Fisher information here. So we're going to have to go directly for the n-dimensional Fisher information, or the Fisher information that depends on all n data points. Okay, so to figure out this, this Fisher information, we're going to need the joint PDF. They are independent, so we do get to multiply. There's only one unknown parameter here, so that's a theta. And because they're independent, as I just said, this is going to be the product as I goes from 1 to n of f sub xi of xi and theta. So usually I don't have the subscript here because there's only one f function and it works for all of the x's, but each one of these f functions is a little bit different. Let me just bring down the distribution so I can remember what it is before I try writing this out. Okay, so let's write out the PDF here. This is the product as I goes from 1 to n, 1 over gamma of alpha, which is gamma of 2, beta to the alpha, which is 1 over theta ci to the 2, xi to the alpha minus 1, e to the minus beta x. So e to the minus 1 over theta, xi over ci, and then an indicator if you like, but we are trying to find a Cremier-Rao lower bound where we need to take some logs and derivatives, and the indicator is just not something you would drag through those calculations. And if the indicator does not contain the unknown parameter, in this case theta, it's just really not something you have to worry about at all. If it does contain theta, then the Cremier-Rao lower bound may not apply. Okay, so I'm just gonna leave that off just so the slide isn't that busy. Now, gamma of 2 is 1 factorial, so that is 1, so that part will disappear. And I'm going to multiply this out. I have 1 over theta squared, and I get that repeated n times, so I have 1 over theta to the 2n. And then I have a ci squared and an xi to the first power. So I'm going to take the product of those and kind of write that as a little chunk. The product as I goes from 1 to n of, I think we already did this when finding the MLE, but since we're dragging this problem over 2 lectures, maybe it's not a bad idea that I write it again. And then finally, the e part, when I multiply those, I get e to the minus 1 over theta, the sum of the xi over ci. So there is the joint PDF, and that sum goes from 1 to n. I want to write down the n-dimensional Fisher information. This is the expected value of the derivative with respect to theta of the log of the joint PDF And this whole thing inside the expectation is squared, or this is also the negative of the expected value of the second derivative, but without the square. So I'm going to take the first derivative and see how bad it is and see if I think it would get better if I took the second derivative. So I'm trying to build up either one of these expressions, and here is the joint PDF. So let's go and take the log. The log of the joint PDF. Here I've got a theta to the negative 2n. So this is negative 2n log theta plus, like this product and this product, I'm going to separate into a sum of logs. So plus the log of this product, which of course is a sum of logs. And you might go ahead and write that right now and not write this intermediate step. And then the log of the E term, which will give us minus 1 over theta, the sum as I goes from 1 to n of xi over ci. The reason I didn't bother rewriting that middle term by pulling that product out to making it a sum is because I'm going to take this derivative with respect to theta, and that middle term has no thetas, so it's going to go away. So I don't really care that I wrote it conveniently or not because it's about to disappear no matter how we wrote it. This derivative is minus 2n over theta. The center term has no theta, that derivative is 0. And the final term is like negative theta to the negative 1. So you'll get negative theta to the negative 2. You'll end up with plus 1 over theta squared. The sum as I goes from 1 to n of xi over ci. Okay, so we are going to square this and take an expectation. And very often we have opted to not square this and take an expectation, but to move to the second derivative. Because the second derivative is often a simpler function, it's not really going to be simpler here, but I guess we could do it. It's not as if those thetas are disappearing or any x's are disappearing. I guess it's still going to be simpler. So, for whatever it is worth, should we do it both ways? Now, let's just do the second derivative way. So the second derivative with respect to theta, this theta to the minus 1 is going to give us negative theta to the minus 2. So we'll end up with 2n over theta squared. And then over here, this is like a theta to the negative 2. So we'll get negative 2 over theta cubed, the sum as I goes from 1 to n of xi over ci. Okay, so the n-dimensional Fisher information is the negative of the expected value of this. 2n over theta squared minus 2 over theta cubed, the sum as I goes from 1 to n of capital Xi over Ci. When you're getting to the actual information, it is the expected value of something with randomness in it. I didn't really make these capital back here because I was just doing algebra. So running this expectation across, you get the expected value of a constant, which is just the constant. So I've got this negative way out front, then 2n over theta squared, negative 2 over theta cubed. The expectation can come inside the sum. The 1 over ci can come outside of the expectation. So we've got something like this. And you'll recall that our expected value, maybe wait, I didn't write this, I didn't recap this, but the expected value of x sub I is going to be 2 divided by that beta parameter, which is going to end up being 2 times ci theta. So this right here is 2 ci theta. Okay, so this ci is going to cancel with this ci. This 2 is in the numerator. It might look a little funny because I wrote it at the bottom here. But it appears that overall we've got negative 2n over theta squared, and then um, positive 2 over theta squared 2n theta. So I get a little cancellation there. I've got 4n over theta squared minus 2n over theta squared. So 2n over theta squared. Just for practice, I mean, you can do whatever you want, but I would suggest you maybe trying the expectation using this formula instead of the second derivative formula, just for practice with your means and variances and finding expectations. But it came out relatively simple. This again is the n-dimensional Fisher information. So to sum it up, the Cremier-Rao lower bound for the variance of all unbiased estimators for theta is 1 over this Fisher information. This is theta squared over 2n, and that's exactly what we got for the variance of our MLE estimator. So yes, the variance of the maximum likelihood estimator achieves the Cremier-Rao lower bound for the variance of all unbiased estimators for theta. And that's the end of part B. Okay, so I have one more part, part C. We're going to try to take some of the new things we learned about MLEs to maybe help us do a hypothesis test. So let's do a hypothesis test for the null hypothesis is going to be that theta is some fixed theta naught, and the alternative is going to be that theta is greater than theta naught, and theta naught is fixed and known. And let's derive a test of size or level of significance alpha for these based on the MLE. So there's always step one in a hypothesis test, which is to choose a statistic that you're going to work with. And here, let's work with the MLE. So that again is step one. I want to choose a statistic, and we're going to choose theta hat is 1 over 2n, the sum as I goes from 1 to n of capital Xi over Ci. Step 2 is for us to write down the form of the test. So here's where you say, I'm going to take the statistic and I'm going to reject the null hypothesis in favor of the alternative if it's in some region. Right now, we're doing pretty simplistic regions. It's usually if it's large or small or both large and small. So look at this statistic. What would be the effect on this statistic if the true theta was really greater than theta naught and not equal to theta naught? The mean for xi is 2 theta ci. So you can see as theta gets large, each xi will tend to get large, which means that each xi will tend to get large and this overall sum will tend to get large. So I will see evidence for this alternative hypothesis being true if I grab my data and compute the actual numerical value of this and it is large. So that's going to be the form of my test. We're going to reject the null hypothesis in favor of the alternative if the MLE is greater than C for some C to be determined. Okay, step 3, we are going to find C. This is where you use your alpha, your size or level of significance of your test. Because I have a simple null hypothesis here, this step is pretty simple. Alpha is going to be the probability of making a type 1 error. You could also say it's going to be the maximum probability of making a type 1 error, and that maximum is taken over all values for which the null hypothesis is true. Because there's only one value there, I don't have to take a maximum over anything, so I'm not even going to write that maximum. The type 1 error says you reject the null hypothesis when you shouldn't because it's true. Rejection for us means that the MLE turns out to be greater than this cutoff C. When it's true means the parameter is theta naught. That's the value given by the null hypothesis. That's the value of theta when the null hypothesis is true. Okay, so how do we compute this probability? We may not be able to do it exactly, and if we can't, then we're going to use asymptotic normality of the MLE. But we might be able to do this one exactly. So let's look into the distribution of this thing. The theta hat, recall again, is 1 over 2n, the sum, as I goes from 1 to n, of xi over ci, and xi has a gamma distribution with parameters 2 and 1 over theta ci. So what is the distribution of xi over ci? We have seen, let me do a parenthetical here, that if x has a gamma distribution with parameters alpha and beta, and if c is a positive constant, then in our parameterization, if you multiply the gamma times c, you still get a gamma and it ends up under the second parameter. So you get a new inverse scale parameter. Because of this, I know that xi over ci, which is like multiplying by 1 over ci, I'm actually going to get a gamma distribution with parameters 2 and 1 over theta ci over 1 over ci. You don't have to write it out like that. If you realize what's happening here, that's going to flip up, and we get gamma 2 1 over theta. This is really good news for us to be able to continue this problem without having to resort to asymptotic normality because it's a nice gamma distribution. And we do know that the sum of IID gamma random variables is gamma, but if, well, let me just tell you that it's easy to show using moment generating functions that if you're summing gamma random variables, if they have the same beta parameter, they can have different alpha parameters, and that sum will still be a gamma, but not the other way around. You know, the moment generating function for a sum is the product of the individual moment generating functions. So going back to alphas and betas, if we're looking at like a beta over beta minus t to the alpha 1 times a beta over beta minus t to the alpha 2, that product of moment generating functions is still going to be beta over beta minus t to the sum of the alphas. But if instead the alphas were the same, or even if they were different, if the betas are different, this is not going to be able to be put into the form like a beta 3 over beta 3 minus t. Yes, the beta 1 and beta 2 could be multiplied together under the same alpha exponent, but you're not going to be able to get the denominator into this form. So if we had different betas, like it appears we have here, the sum of those gamma random variables is not going to be another gamma. But after doing this kind of transformation, we actually did end up with gamma random variables that have the same beta. So we were lucky. Again, if we did not have a nice gamma distribution here, we would have to use asymptotic normality, which, by the way, I'm going to use anyway. So we can compare how this test would have come out if we did it with asymptotic normality. Okay, so what am I trying to say here? These are all IID now. They're gamma 2, 1 over theta. And when you sum IID gammas, you get just, we'd have a 1 over 1 over theta minus t squared raised to the nth power. So we get that to the 2n power. And so this entire sum is gamma 2n 1 over theta. Now let's bring this constant in. It will end up underneath the second parameter. And so we end up with the MLE has a gamma distribution with parameters 2n and then 2n over theta. That's the distribution of our MLE. We can find it exactly. So if you want to do a hypothesis test using the gamma distribution, we don't know exact critical values in closed form. We can't do the integrals we need, so we would have to find them numerically. In statistics, we usually try to force everything towards a chi-squared or normal or something we can work with. And that's what I'm going to do here. I'm going to turn this into a chi-squared random variable. Remember that if x has a chi-squared distribution with n degrees of freedom, that means that x has a gamma n over 2 1/2. And I kind of always write this 2n as like 4n over 2. So I really need to get that second parameter to be 1/2. If I multiply by something over here, it ends up underneath this. So let's, you probably want to do this all at once, but if I multiply by 2n over theta, I get a gamma 2n 1. That's just to get rid of this, but we also want a 1/2 there. So I need to multiply by like another 2 to get that there. So what this is telling me is that 4n theta hat over theta has a gamma 4n over 2 comma 1/2 distribution, which is a chi-squared 4n. So this depends on the unknown theta, but that's okay. We're doing a hypothesis test, but much like a confidence interval, we are working through a pivotal quantity, which is some function of the statistic and the unknown parameter whose distribution is known to you and not depending on any unknown parameters. So back up to our alpha statement. Alpha was the probability that theta hat was greater than c when the parameter was theta naught. So all of the stuff I just did to find the distribution of theta hat did depend on the parameter being theta. So I don't want to multiply by this. I really want to multiply by 4n over theta naught, because in this probability statement I've just written, theta is theta naught. So if I write 4n over theta naught times the MLE, do the same thing to both sides, and the parameter theta naught is, if you look at the parameter space for the gamma distribution, this is a positive parameter, so nothing's going to flip. Then we get this has a chi-squared distribution, and this is just some number. And this is now irrelevant to the probability we want to compute because that chi-squared distribution does not depend on the fact that theta is theta naught. So here's where we write something like W greater than 4n over theta naught c, where W has a chi-squared 4n distribution. And I want to be above something with probability alpha. So if we look at a chi-squared 4n PDF, the number that will be above with probability alpha, we call this chi-squared alpha comma 4n, or you might call it something else, but that's the notation I've been using in here. So the subscript alpha is representing area to the right of the critical value, and then some way to show the degrees of freedom. That is the number that the chi-squared 4n is above with probability alpha. So this means that 4n over theta naught c must equal this critical value. And so c is theta naught over 4n times this chi-squared critical value. So let's bring it all home in step 4. What is the test? The test of size or level of significance alpha for the null hypothesis that theta equals theta naught versus the alternative that theta is greater than theta naught for this given distribution is to reject the null hypothesis in favor of the alternative. It's important that you write that part because you'll notice that we have not covered the entire parameter space. So what happened to the theta less than theta naught? We're not considering that. We're assuming that this null hypothesis is true, and we're rejecting it in favor of this alternative if our MLE is kind of large. So because the null and alternative hypotheses do not make up the entire parameter space, it is kind of important to say this part. If the MLE is greater than theta naught over 4n times this chi-squared sub alpha comma 4n, and that's a fine answer, but you might want to give it in terms of the statistic. Remember, this is 1 over 2n. The sum as I goes from 1 to n, xi over ci. So there is your recipe for the person that wants to do the test. They will observe some x's. They will presumably know the n's and the c's, so they can compute this quantity and compare it to this quantity. Okay, so there is an exact hypothesis test. But suppose we couldn't figure out that chi-squared distribution. I was a little worried that when we looked at the distribution of xi over ci, we were actually going to get a gamma distribution that still depended on ci. So they were not IID, and the sum of non-IID gamma random variables may not be gamma and is nothing nice that we can work with. So I want to also, or let's say alternatively, find an approximate size alpha hypothesis test based on asymptotic normality of the maximum likelihood estimator. So this would assume a large sample because this is a result that only holds for n in the limit, and so it will approximately hold for large n. And we'll take a look at how large n needs to be. So we know that MLEs, for the most part, because we did have some conditions we needed, are asymptotically normal, and they have the correct, so the theta that you're trying to estimate as the mean, and the Cremier-Rao lower bound for the thing you're trying to estimate. When we proved this, we used theta naughts because I was really trying to fix a theta that generated the data, theta naught, and then use theta as a variable for all our proofs in the functions that were likelihoods. The probabilities we need to compute in our hypothesis test are probabilities that are always in the case where the null hypothesis is true. So we could say like under H naught, when the null hypothesis is true, the MLE is asymptotically normal with mean theta naught because the null hypothesis said that theta was equal to theta naught, and the Cremier-Rao lower bound for the variance of all unbiased estimators of theta naught. Right. So the hypothesis test, we're still going to start with that MLE. I won't write out the steps again. Step 1 is to choose a statistic. And in this alternate version, we're trying to do a second hypothesis test based on the MLE using asymptotic normality. Step 2 is going to be the form of the test. and nothing has changed there. So we're still going to come to step 3, where we have alpha is the probability that the MLE is greater than some C when the null hypothesis is true. Okay, so everything was the same in this hypothesis test up until now. In the test we just finished, we multiplied by some stuff to turn everything into a chi-squared so we can give a test based on chi-squared critical values. But now I want to use normality. So I want to go from this approximately normal thing, assuming a large N, and standardize this to an approximate standard normal. So this is the probability that if we take away the mean for that normal, which is right here, and we divide by the variance and do the same thing to both sides, trying to use normality. So I want to compute this probability by standardizing it to a standard normal. Then this is approximately the probability that Z is greater than something where Z is standard normal. Or you could say it's exactly equal where Z is approximately standard normal. I'm going to leave it like this. The Cramér-Rao lower bound was specifically theta squared over 2n. And now I no longer need this because the distribution does not depend on that parameter. And so looking at a standard normal, a z-curve, I want to be above a number with probability alpha, and we call that critical value lowercase z sub alpha. So in this case, we're going to need c minus theta naught over, I'm going to go ahead and take the square root here. Theta, because it's a positive parameter, so you don't have to worry about a plus or minus, over the square root of 2n must equal this lowercase z sub alpha, the critical value that cuts off area alpha under the standard normal curve and to the right. So this means that C is theta naught plus Z sub alpha. Yikes. This, get a color here. This should have been a theta naught squared, and this should be a theta naught. Let me fix that. Okay, so times theta naught over the square root of 2n. So to finish this off, the approximate large sample, the rule of thumb is n greater than 30, but that's a rule of thumb that's supposed to take care of, well, this isn't even a central limit theorem. This is an approximate normal distribution for the MLE. People are still going to use greater than 30. I don't think it's the greatest rule of thumb, and it will depend on the underlying distribution, and we're going to look at it. So approximate large sample test of size alpha for the null hypothesis that theta equals theta naught versus the alternative that theta is greater than theta naught is to reject null hypothesis in favor of the alternative if the MLE is greater than theta naught plus Z sub alpha theta naught over the square root of 2n. We had an exact test and an approximate test. They both have us looking at theta naught, right? One has us rejecting if this is true. That's the exact test. And this one has us rejecting if this is true. So are they going to give us the same result? They should be approximately the same for large n. So what I'm about to do is to show you what this value is and what this value is for various n. And in order to do that, I'm going to fix an alpha so we can just look at it numerically, and I'm going to fix a theta naught. So let's fix our theta naught, our null hypothesis value, to be 3 and alpha to be 0.05. I can then look up these critical values, The critical value for the chi-square does depend on n, and I'm going to look it up for every n. And I have a graph for you, so let me switch screens here. Okay, so what you're seeing here, I'll have to zoom in. I'll zoom in eventually, but I have n on the x-axis, and I have the cutoff, the value that the MLE needs to be above before you reject the null hypothesis in two cases. So I've got a bunch of black dots, and that represents the exact test, and the red dots represent the approximate test. So like if n is only 1, the black and red dots are far apart. So the exact test says reject when you're above this number, like 5.8-ish. And the approximate test says, no, don't reject until you're above, I don't know, 6.5-ish. So they're kind of far apart. But as n gets larger, you can see that they're almost falling on top of each other. Now I could change the scale on the y-axis, so those will look separate. But you can keep going on out for, even larger n, and they'll get closer and closer and closer. So depending on the kind of accuracy you're after, um, that would be how large you would really need to go for that approximate test to be as good as the exact test. And I went out to n equals 500 and got the two cutoffs. One test says reject if the MLE is greater than this number, and the other says reject if it's greater than this other number. I got those numbers to match within 6 decimal places when I got out into the 400, 500 range. So at that point, you probably aren't going to be able to tell the difference between the test and, you work with what you have. You work with the data you have, but um, in an ideal world, you could say, I only have this much accuracy. My measurements are only to this accuracy. And then you could make these tests totally equivalent if you prescribed a large enough N. But they're pretty good. I mean, scale is everything, right? So it's hard to see on this graph, but they're pretty good, before N equals 100, around here at around, I don't know, 77 or so, 75. So yeah, there's exact and approximate in action and how they compare. So you've waited long enough. We are now in UMVUE territory. UMVUE is an acronym that stands for Uniformly Minimum Variance Unbiased Estimator. So we're ending the MLE section of the course, but we're not leaving the MLEs behind. We're going to use them every day. We still have a lot to talk about with MLEs, but we're moving to another form of estimation. So we had the common sense estimation where you're just kind of guessing and maybe adjusting things to make them unbiased. Then we had method of moments, where you equated population moments with sample moments. Then we had maximum likelihood estimation, and we've spent quite a while in there. And now we're going to this UMVUE thing. So what is the UMVUE? It stands for Uniformly Minimum Variance Unbiased Estimator or Estimation, UMVUE. Some people in books will not have the E on the end because they're just, they'll say it's a UMVUE estimator. Some people will not have the initial U and they'll just say UMVUE, but they do mean the same thing we mean, but they're not emphasizing the uniformly. So we are not, I made this look like we're getting in here now. We're not. We have quite a bit to build up, so I'll call this towards the UMVUE. I want to describe what an UMVUE is. If we are estimating a parameter theta, or maybe a function, a tau of theta, and we have two unbiased estimators, I'll call them theta 1 hat and theta 2 hat. They're both unbiased, so we've already got that. They've got that going for them. So let's look at the variances. When you compute the variance of your estimator, these are almost always a function of theta, unless you did some, I estimate it to be 17, no matter what you say and no matter what you see. unless you do something kind of silly, these are functions of theta. For example, our last MLE, the variance was theta squared over 2n. So suppose you were comparing two unbiased estimators in terms of their variance. I don't mean it to, in this picture, I'm going to have a theta axis and maybe theta is positive. I don't know. But suppose you sketched like a graph of the variance of your first estimator as a function of theta versus the variance of your second unbiased estimator as a function of, both as a function of theta. Let me fix this, make this axis a little longer. So what you can say is that the theta 1 estimator is better in that it has lower variance here in this region. This is the region on the theta axis for which the first estimator is better in terms of lower variance. And then out here, the second estimator is better because it has lower variance. The problem with this is you don't know what theta is. That's the entire reason you're estimating it. So looking at these two variances, I cannot say one has a better estimator than the other uniformly in theta. Maybe you recall the definition of a continuous function, f. You take some epsilon greater than 0, and you look within epsilon of f of x, and you say, I can find a delta such that if I'm taking a point within delta of epsilon, I fall in that epsilon neighborhood of f of x. But your delta can change depending on where x is. But if you get one delta that works for all x, you talk about uniform continuity. Uniform in math means for all. And a uniformly minimum variance unbiased estimator is going to be something down here that has lowest variance no matter what theta is. So it's good because you don't know what theta is. You can say this is the best no matter what theta is. Uniformly in theta, for all theta, the smallest variance when you look at the variance of all possible unbiased estimators for theta. Yeah, it's just that cool. So we are a few days away from figuring out how to find an UMVUE. We are starting with some building blocks today. And the first thing I want to talk about is the concept, well, actually before this, I got to do a little review. So the first thing we're going to talk about is something known as sufficient statistics. And the concept of sufficiency does depend on conditional probability. So let me remind you about conditional probability and conditional PDFs really quickly. You usually first learn about it in terms of events. So if I have a deck of 52 American playing cards and they're shuffled and I randomly select a card and I'm not showing it to you, but I say, what is the probability? It's a king. You know that there are 4 kings in 52 cards, and they're all equally likely if I truly randomly selected one. So the probability of getting a king is 4 out of 52 or 1/13. So let's draw a card at random from a deck of 52 American playing cards. The probability you get a king is you have 4 chances out of 52. Right? But if I randomly select that card and I'm not showing it to you, I've got the back towards you and I say, it's a face card. It's a card with a face on it. Now what is the probability it's a king? Your answer is going to change because I've narrowed down the possibilities for you. There are 12 face cards in a deck of 52 American playing cards. There are 4 jacks, 4 queens, and 4 kings. So if I tell you it's one of those, now you have 4 out of 12, right? You have 4 of 12 chances to get the king. So the probability it's a king, given some information that it's a face card, is 4 out of 12, or 1/3. That's a conditional probability where you're given some information. And I'm sure you've all seen this before. I'm not exactly sure, or I wouldn't be talking about it, but this is probably insulting to you. I'm not going to spend too long here. But the way we would write this is a vertical line representing the given and then the two events. And when you start probability, you usually start in terms of events. So you let like A and B be events, like A could be the event that you get a king and B could be the event that you get a face card. And we're trying to compute a conditional probability that A occurs given that B occurs. Venn diagrams are definitely your friend when trying to come up with some basic rules of probability. If I draw a couple of circles representing these events, and I tell you that an outcome of my experiment landed somewhere in B here, given that it's in there, what's the probability that it's an A? That's just a fraction of this probability or area. The definition of this conditional probability is going to be the probability of A intersect B over the probability of B. That's how you define conditional probability. And of course, you want to assume that the denominator is something that can happen with a positive probability, but you're usually okay because this is always in the context of you observe that something happened. Now, what is the probability this other thing happens? So if you can possibly observe it, then it has to have some positive probability of happening. Okay, in terms of random variables, if we have discrete random variables, then we can talk about the probability that x equals some x given that y equals some y. And it's just going to mimic the definition we just saw. This is going to be the probability that x equals x, and a comma in probability is and y equals y over that marginal probability that y equals y. And this is a conditional probability mass function. We have a probability mass function for discrete random variables, a probability density function for continuous ones. I tend to call them all PDFs, but know that they mean different things. But you can give this a notation like the PDF for x given y at some argument little x given some argument little y. So use that as this definition. So this is a conditional probability mass function or probability density function if you're like me and you use the terminology. You're a little sloppy with your terminology. So in the continuous case, in the interest of time, I'm just going to jump to the point here. The conditional PDF for x given y is no longer probability, just like it's not a PDF for any continuous random variable doesn't represent probability. It represents a curve under which area represents probability, or in higher dimensions, a surface under which volume represents probability. This is, if these are one-dimensional, a curve under which area represents probability. So if you want to find the probability that x is less than or equal to 3, given y equals 2.1, I do have something to say about this. This is going to be the integral minus infinity to 3 of this conditional PDF integrated over x. If this concerns you, I don't blame you. If x and y are continuous, how can y equal 2.1? Before you measure it, the probability that you're going to observe that 2.1 is 0. We're assuming usually we can measure things with infinite accuracy when we're talking about continuous random variables. And so if you're measuring the length of some fish you're catching, the probability you're going to get one that's exactly 2.1, say, inches long is going to be zero, because the chance of hitting that number exactly is zero, right? There's just so many possibilities if you can measure with infinite accuracy. But assuming you can measure with infinite accuracy, once you've observed it, if you observe a fish that has length 2.1 inches, then you have. That's been observed. And it's okay for continuous random variables to be equal to numbers if you are on the right side of the conditional line. If this was x equals 3, the whole probability would be 0. The probability of seeing that would be 0. But once it's measured and fixed, then you have observed that. And so there's no could you ever observe that? You have. So again, even though y is continuous, it does make sense to say y equals 2.1 as long as it's after the conditional line. So how do we get this? We get this analogously to what we did up here. This is our notation for this. And this is kind of messy, I'm sorry. And we can write it in terms of PDFs. Using this would be the joint PDF over the marginal PDF for y. And that definition still holds, even if x and y are continuous. So we get a joint PDF, which does not represent probability, over a marginal PDF for y, which does not represent probability. But this is how you define a conditional PDF in the continuous case. So that would be how you would compute something like this in order to compute something like this. Okay, so that was a very quick refresher on conditional probability. Let's get back to our machinery for the UMVUE. Let's talk about sufficient statistics. Suppose we have, let's say, a nice simple model. We have x1 through xn, IID, Bernoulli, which means they take on the values 0 and 1, with a parameter p. And we want to estimate p. So you're right here and you want to estimate p, but the data, the observed values of x1 through xn are in another room, and I have to go out there and bring them to you. So they're heavy, they're bulky, they're piled in my arms, I'm dropping them everywhere, and I say to you, look, you're trying to estimate p. What are you going to do? You're going to compute the proportion of ones, probably. You could estimate it poorly as well. You could do almost anything. But you're probably going to compute the proportion of ones you see. And we can get that from the sample mean by adding up all the ones and zeros and dividing by n. So I would say to you, do I really need to bring in all that data, all those individual pieces that are falling everywhere, or is it enough? Is it sufficient that I bring you one statistic? So is it sufficient to look only at the statistic, I'm going to call it t, the sum as I goes from 1 to n of the sum, instead of all x1 through xn? This is the idea behind sufficiency. It's going to be, can you reduce the dimensionality of the data into a statistic, or maybe 2 or 3 statistics that are enough for you to not lose information about P? And what is that information? Because I just said an estimator could be anything. You could have a very bad estimator that doesn't have like common sense attached to it. And maybe you're not going to use the sum of the x's. But I need to define sufficiency formally. I'm about to do that, but that's the idea. A statistic or a pair of statistics would be, or a triple or whatever, would be sufficient if You had those instead of the original data and did not lose any information about P. And I need to quantify not losing information about P right now. Okay, so here is a definition. Suppose we have x1 through xn with a joint PDF f of the vector x and theta, which for us is probably a product of individual things, probably x1 through xn are IID. The statistic, instead of calling it T, I'm going to call it S for sufficient. And this is going to be some function of the data. And it actually can be a two-dimensional function of the data or a three-dimensional function of the data. So as an example over here, a statistic might be the sum of the x's. A vector of statistics might be the sum of the x's and the sum of the x's squared. Anything you want, any different functions, and we can have any dimension here. The statistic could actually be the n-dimensional statistic, which is bring me all the data. But the statistic is sufficient for, we usually say for theta, but I'm going to say for estimating theta if the joint distribution of x1 through xn given conditional on knowing the value of the statistic, so given that s equals some value, does not depend on the unknown theta. That's like one way of saying, given that you've seen this, this does not have any more information about theta in it. So let's go back to our Bernoulli example and try this definition to show formally that the statistic, the sum of the x's, is sufficient for estimating P for the Bernoulli distribution. So we would say sufficient for P, sufficient for estimating P, or sufficient for the Bernoulli distribution, or overall, the best way to encompass it all is sufficient for the model. Because if the joint PDF for the x's given the statistic does not depend on P or theta, also does not depend on P squared or theta squared, and so it would be sufficient as well for estimating functions of the parameter. I think I made that more complicated than it needed to be. Let's just try to follow the definition for the Bernoulli distribution. So here is an example. I have x1 through xn, IID, Bernoulli with some parameter p. Let's show using this definition, because we're going to have quicker ways to do this, that S defined to be the sum as I goes from 1 to n of the xi is sufficient. Now, again, I was just saying sufficient for P, sufficient for estimating P, sufficient for estimating functions of P, sufficient for the Bernoulli distribution, because you might have another distribution with a parameter P for which this is not sufficient. So overall, we usually say sufficient for the model. Okay, I want to show this using the definition. So yeah, let's do it. The probability, I want to look at the joint distribution of x1 through xn, given the sufficient statistic has been fixed for us. And so because things are discrete, I can write this as probabilities. I'm going to look at the joint probability that capital X1 equals little x1 through capital Xn equals little xn, given s equals some little s. How would you compute this probability? We just talked about this. This is like an A given B. you would rewrite this as the probability of the first thing intersected with the second thing. So that's really an n plus 1 way intersection. So I can write this as x1 equals little x1 out through xn equals little xn, comma, and s equals s over the marginal probability that s equals s. That's how we would define that. The s here is the sum of the x's. I think we did this way back when, but what is the distribution for the sum of Bernoulli random variables, IID ones? This is a job for moment generating functions. If you take the moment generating function for the Bernoulli distribution, which you can find in your table, and raise that to the nth power, you'll see the moment generating function for the binomial distribution with parameters n and p. So S as the sum as I goes from 1 to n of these Bernoullis has a binomial distribution with parameters n and p. And again, if you don't believe that or already know that, then check it out using moment generating functions. So I can write that probability in the denominator, but first let's deal with that numerator. Note that the little x1 through little xn and the little s, these are just arguments for a function we're computing a probability for. And the capital S is definitely the sum of the capital X's, but the little s is whatever you plugged it in to be. It's not necessarily the sum of the little x's. So let me make this into a smaller aside problem. What is the probability that x1 equals 3? This is not the Bernoulli because those are only zeros and ones. x2 equals 4, and x1 plus x2 equals 7. In this case, this is redundant information. This is going to be the same thing as the probability that x1 equals 3 and x2 equals 4. And if they're independent, then you can break this up into a product of probabilities and go, go, go. And I don't know what distribution this is, so I can't really do much more. But what if you were looking at the probability that x1 equals 3, x2 equals 4, and x1 plus x2 equals 0? That can't happen. This probability is just going to be 0. You can't have this, this, and this happen at the same time. So going back up to what I actually care about here, move this, I'm going to need this space. Close this parenthesis. We know that capital S is the sum of the capital X's. This probability here is going to be 0 if little s does not equal the sum of the little x's. I'm just sort of exaggerating my symbols so you can see that that's a lowercase s and lowercase x's. And then it's something else if little s is actually equal to the sum of the little x's. In that case, this is redundant information that we can just drop, like I dropped the fact that x1 plus x2 is equal to 7. So we get two cases. In this case, you'll note that there is no parameter p here. So this is free of the parameter, theta free, or in this case, p free. But we have to consider this other case. So let's do it. So I'm going to write, I guess I'm going to rewrite this. The probability that x1 equals x1 out through xn equals xn, and s equals s over the probability that s equals s. In the case where little s is equal to the sum as I goes from 1 to n of the little xi, this thing is equal to the probability that x1 equals x1 out through xn equals xn, and I don't need to write this, it's redundant, divided by the probability that s equals s. And then let's compute this probability. These are IID. So the top, I can break this up into a product. I only need one of the i's for that. I need them to be independent. And this is the Bernoulli probability. So for the Bernoulli random variable with parameter p, the probability that x equals x could be 0 or 1, and we get p to the x, 1 minus p to the 1 minus x, and an indicator that says that x has to be one of the two values in the discrete set, 0 and 1. Indicators are important here because they're important when we wanted to show independence. We said you can factor a joint PDF completely separated into an X part and a Y part, and that includes the indicators. Here I want to say this doesn't depend on the unknown parameter, and that includes the indicators. There could be dependence in there. So the indicators are kind of important here. What I have is little p to the x1, 1 minus p to the 1 minus x1, and an indicator that says that x1 is is in the discrete set 0, 1, multiplied all the way out to p to the xn, 1 minus p to the 1 minus xn. An indicator saying that xn is in the discrete set 0 to 1. And then down here, I want to use the fact that S has a binomial distribution with parameters n and p. So the probability that binomial is equal to S. This is going to be n choose S, p to the S, 1 minus p to the n minus S, and an indicator saying that S has to be in the set 0, 1, 2, up through n. There's the binomial PDF. Right now, this ratio appears to depend on p, but yeah, let's move things around. Let's put all of these p's together. So I'll get p to the sum of the xi and all of the 1 minus p's together. So I'll get 1 minus p to the n minus the sum of the xi, and then a product of indicators. And down here, I have n choose s, p to the s, 1 minus p to the n minus s, and then another indicator. And I don't care to get this to be something clean. I just want to get rid of the p's. But we are in the case where little s is equal to the sum of the little x's. And that means that I'm going to get cancellation here and here, since little s is equal to the sum of the little x's. I'm also going to get cancellation here and here. And I don't care that I'm not canceling out the rest of it. For the record, I'm going to write this as a product as I goes from 1 to n of the indicator over an n choose s and an indicator for s. And this, there's no p in here. This doesn't depend on p. So in conclusion, we looked at the probability that x1 equals little x1 out through xn equals little xn, given s equals s, and we got, move down here, we got 0 if little s does not equal the sum of the little x's, and then we got this thing. Let me copy and paste this. If little s equals the sum of the little x's, but this entire thing does not depend on p. So we looked at the joint distribution of all of the x's given this statistic. We got something that does not depend on p, and this implies that the statistic s, which is the sum as I goes from 1 to n of the xi, is a sufficient statistic for this model, for the Bernoulli distribution, for estimating P or any function of P for the Bernoulli distribution. That was a lot of work. That was showing sufficiency by definition. I have a few minutes left, so fortunately, you're not going to have to do this again and again and again. You know what? Before talking about that, if the sum of the x's is sufficient for the model, then throwing in an extra statistic, say, suppose I, from the hallway, bring you not the individual x's, but the sum of the x's and the sum of the x's squared. That's like a two-dimensional statistic. Is that enough for you to estimate the parameter? That is not going to drag dependence on P into this probability. It is more than enough. It is more than sufficient. And I did hint earlier that having all of the data is sufficient. What would that look like in terms of conditional probability? So, thought break, this is not the Bernoulli, but for any discrete distribution, the statistic, the n-dimensional statistic, this is always sufficient for estimating whatever parameter you're estimating. Because you might have x1 through xn, IID from some distribution that depends on a parameter theta. And if you want to look at the joint probabilities for x1 through xn, given that these values have been given to you, this is going to be, regardless of what you started with, this is going to be 1 if x1 equals s1, x2 equals s2, xn equals sn, and it's going to be 0 otherwise. You know, it's kind of like saying, what is the probability that x1 equals 3, x2 equals 4, given x1 equals 3 and x2 equals 4? You're given that, so you're definitely going to have x1 equals 3 and x2 equals 4. This probability would be 1, whereas if you kind of messed one of these up, this probability is going to be 0. So this is how you formally prove that given all of the values that have been fixed for you in the data, that's always going to be a sufficient statistic. It's an n-dimensional statistic, but this is theta free. Doesn't depend on theta. So that's how you prove that having all the data is sufficient in lieu of having all the data. Okay, so this thing we just did, showing this conditional probability was not dependent on P or in general theta, that was really messy, and it's going to get worse for different distributions. Fortunately, I have a big shortcut for you next time, and not only will it be a quick way to show something is sufficient, but it will also tell you what statistic you should be looking at in the first place. So rather than me saying x1 through xn or IID Bernoulli show that the sum of the x's is sufficient, it will say x1 through xn or IID Bernoulli, find a sufficient statistic, and along the way show it's sufficient. It's going to pop a statistic out for you. And we've just seen that many things can be sufficient. It's sufficient to have all the data, but our goal is really going to be to kind of reduce the dimensionality. I don't want to bring in all the x's. Can I just bring in the sum of the x's and the sum of the x's each individually squared? Maybe I can only bring in the sum of the x's. We're going to go down to the idea of something that is minimally sufficient. And the reason we care about this is because ultimately we want to find UMVUEs. We want to find uniformly minimum variance unbiased estimators for P, for the Bernoulli distribution, or a general theta. And we're going to see that UMVUEs always depend on any sufficient statistic. So if you can reduce the dimensionality of your data to say, I just want to look at the sum of the x's, if I can prove to you that the UMVUE is going to be a function of that, then you know to limit your search for minimum variance unbiased estimators to sufficient statistics of lower dimension. So it's going to be really important for us to be able to find sufficient statistics and show they're sufficient kind of quickly. And I have a factorization criterion for you coming up next time on mathematical statistics.